Hello, I'm Shichuan Deng, and welcome to my pre-recorded monologue where I talk about our paper, Approximation Algorithms for Clustering with Dynamic Points, which was recently accepted by ESA 2020. So clustering is one of the most fundamental problems in computer science. And let's start with the basics. We are given some items and we are asked to select a number of cluster centers and group the items around the centers. And I'll give some famous examples: k-center, k-median, k-means, k-facility, L-centrum, k-clustering. And here I won't talk about their specific definitions, and I assume everyone is kind of familiar with them. And in this kind of problems, we are usually faced with the trade-off between optimization and some kind of constraint. For example, in k-median, our objective is to minimize the sum of the distances from each item to its assigned center. And our constraint is that we can select at most k-centers. Even in some non-clustering problems, for example, knapsack, we still have such kind of trade-off. Our objective will be to put as much value as possible into the knapsack, and our constraint is that the total weight of the items we are picking should be at most W. And in recent years, there has been some very exciting breakthroughs in clustering problems, and it is now actually a pretty active field of research. And in our paper, we ask the following question: what if things start moving? So let me start with an example. Suppose in the distant future, human beings are well beyond the type 1 civilization and started to utilize the untapped resources in the solar system. And one day they want to detect some minerals may be available for mining in some area of the asteroid belt, which is relatively close to Earth. And some company sends a lot of unmanned drones for this mission. And each drone will follow a specific path during the mission, which means they will be at different locations at different times. And our captain, Smash Creek, he's in charge of the communication between the drones and the ships he's controlling. Because in case there is any data loss, we need to provide a backup to the drones in real time. And he has 1,000 ships that are acting kind of like routers, moving routers to the unmanned drones and provided communication with them. So during the mission, every time some drone detected some area which is rich in some kind of minerals like copper or gold, the data needs to be transmitted back to one of the spaceships our captain is controlling. And the further away it is from the ship, the more energy it consumes to transmit data, which makes sense. And our captain may sometimes want to move his ships around, and because during the mission, some of the drones may get really far away from their original locations. So we might move one or two ships towards their direction so that the energy they need to communicate will be reduced. And of course, we need to spend a certain amount of fuel in order to move our ships around. So the total energy consumed in the mission will be in three parts. The first one is the movement by the drones. The second one is the movement by our ships. And the third one is the communication costs between the drones and the ships. Our captain is kind of a lazy person, but he does not have any control over the movement of drones because they are pre-programmed by other teams. So the only things he can control are the movements of the ships. In consequence, the communication costs between the ships and the drones, depending on the locations of the ships. at a specific time. So there's the trade-off between the less maneuvering and less com cost. And here is the formula for total energy consumed in the mission. And the highlight ones are those parts that are controlled by our captain, which is in charge of the communication and ships. If the drones never move, the setting is the same as classic clustering, or the classic moving facility location problem if you factor in the actual energy the ship is also consuming from the basement to the area where the mission is being taken place. And in our setting, the drones and the ships are both moving. So we have the last two parts of the total energy to optimize or to put constraints on. And for the sake of simplicity, we're only considering this problem on a finite metric spaces and discrete time steps. So following the previous example, we begin with the definition of our first problem, which is dynamic ordered K-median. But I'll first give the definition of the dynamic non-ordered K-median, which is kind of long, but if you focus on the objective we are actually minimizing, it is weighted sum between the first part, which is the total energy used by the drones over all the time steps. And the second part is the movement of our ships between consecutive time steps. And that's why we are using minimum matching to evaluate the movement cost of our ships. And here, at different time steps, we use CT and FT to denote the locations of the clients, or in our case, drone ships, and the potential locations of our facilities, and in our example, the ships. Besides that, if every time step we're also given a non-increasing, non-negative vector, and the first part of our objective is replaced by the weighted sum of the service cost or communication cost, the instance will becoming a dynamic ordered K-median problem. And to solve this problem, we are using a technique which was recently developed in solving ordered K-median problems. And before solving this problem, I would like to briefly introduce the techniques that was used in solving ordered K-median and some other related problems. Suppose we have a series of functions which is mapping from some action space to real values, and a series corresponding weights in descending order. And we want to at least approximate the following objective, which is the usual ordered objective given action A. And here the permutation is used to order the functions so that it is also in descending order. And usually our action space is really large. For example, in K-median, we are asked to select K centers in M locations. And when K is not a constant, it becomes exponential in the input size. But usually the size of D is polynomial and size of the input. For example, if we are, again, optimizing the K-median instance, every function, which is the distance from a point to its closest center, the possible values it is taking is obviously polynomial. So the techniques in finding an approximate solution, first by guessing the maximum value of the function in the optimal solution, and then try to guess the appropriate lengths that are multiplied onto specific breakpoints in the optimal solution. Because the objective is the sum of these distances multiplied by these weights. And obviously, if you want to guess the length for all points from lambda 1 to lambda n, it's not going to work. The space is too large. So we need to figure out a clever way to reduce the size of the breakpoints, meanwhile preserving some of the properties of the optimal solution. So one possible way to construct the set of breakpoints is to consider the actual values of the weights given and round them to the powers of 1 plus epsilon times lambda. There is also another way of taking these breakpoints simply as powers of 2. To illustrate why this works, let us first plot lambda I times f sub sigma y. Because lambda and f are all in decreasing order, we can roughly represent the plot as a decreasing curve. And by taking all these breakpoints of powers of 2, we are actually adding up all these rectangle areas under the curve. But the true objective is actually the area under the curve. So we need to estimate how much area is lost due to our estimation. And it can be seen from the graph that since the curve is decreasing, the gray area, which is lost, is at most the area of the rectangle enclosing it. And because this rectangle has a base of 2 delta and a height less than the rectangle before it, so the total area loss can be bounded using our estimated objective by a constant. So now we have a set of breakpoints of size log n. And because the optimal solution, these breakpoints will be multiplied onto a sequence of lengths, which is also in descending order. And all these possible lengths also has the support of size log n. After we throw away those lengths which are too small, the total number of choices can be bounded by this expression, which is a polynomial. So after we correctly or approximately guess the lengths multiplied to these breakpoints in the optimal solution, we need to construct a linear programming to solve our problem. In the original linear programming, minimizing the objective k-median, we are using a variable xc to represent whether or not we select an edge between a client and a facility. And after guessing these values corresponding to the breakpoints, we simply modify the objective by pre-multiplying the weights onto these different lengths. And it can be shown that solving this modified LP gives us constant approximations to the optimal solution, as long as our guess values corresponding to these breakpoints are approximately equal to those in the optimal solution. And here is our LP, where x sub ij of t indicates whether or not we serve the client j using I at time t, and y sub I t indicates whether to put a facility at location I at time t, and z sub I prime t indicates whether to move a facility from location I, which is in time t, to location I prime, which is in time t plus 1. So we solved the LP. But what's different from traditional LP solving for k-median problems, we are actually allowing the use of multisets at different time steps. So what does it mean? It means at any given time, there might be multiple facilities residing at the same location. So we simply remove the constraint and allow yi to be bigger than 1 for any I. And if the LP solution gives y sub I bigger than 1, we simply make copies of it so that every variable is at most 1. And after solving the LP and making copies of facility locations, we do the usual stuff for solving k-median using linear programming. For every time step, we remove some of the clients that are relatively close to each other. For every remaining client, we group some constant volume of facilities around it and call it a bundle. And after making these bundles, make some pairs of the bundles. And usually using some kind of dependent rounding techniques to get an integral solution. But in our problem, the locations of every facility at every time step is also interconnected by the movement of these facilities. So we need to find a way to run the movement variables and facility location variables at the same time. So we design a network and embed the previously solved fractional solution as a fractional flow on the network. And our attempt is to round this fractional flow into an integral flow, which can be used to represent an integral solution overall. The reason why we can do this is because the network is defined so that the matrix defining it is a total unimodular matrix, and the capacities of edges are also constrained by integers. So the polytope representing the solutions of this network is integral. And let's briefly review how the network is constructed. For every time step, we add 6 interconnected layers from left to right, and we call this a block. The first and last layer of this block represent all the possible locations of facilities in this time step, so that neighboring blocks can be connected directly by the movement variables that was defined in the linear program. The reason why we include 4 more layers between the first and the last is to limit the number of facilities that can be chosen within each pair and within each bundle by adding all these edges and putting integer upper bounds on these capacities. So the whole network is constructed by adding all T blocks and connect them one after another. And the solution from the LP previously is naturally a flow of value k on this network. Since the flow polytope is integral, we can express the fractional flow as a convex combination of integral points of this polytope. And the number of these extreme points is also polynomial in the size of the network. So if we randomly round the fractional flow into an integral flow according to this convex combination, the marginal performance of every edge will be preserved. And because our objective is the sum of these performances, its total expectation is also preserved. And in fact, we can give 2 different results from this rounding of the LP solution. The first one is when there are only 2 time steps, we can construct a 48 plus 20 square root of 3 approximation for the dynamic order k-medium problem. And when t is a constant but larger than 2, we have an additional constraint on the minimal weight values over all time steps. And if this value is epsilon prime, our approximation ratio will be 48 plus 20 square root of 3 plus O epsilon plus O 1 over epsilon prime times gamma. So if the weight vectors are given and we are mixing k-medium instances together with k-centered instances, this instance cannot be solved using our algorithm because in this case the minimal weight value given is 0 in the k-centered instance. There are also a lot of more technical details on how this rounded solution can actually preserve the marginal distance for every client, as well as how, if the rounded integral flow is inconsistent at every time step, how we can fix the issue by rerouting some of the flow manually. The second problem we are considering is called dynamic k-Supplier, whose definition is very similar to the previous one, but this time we are given an additional constraint. The objective we are trying to minimize is effectively doing all k-Supplier at every time step and taking the maximum over all time steps. And the constraint is given by a constant b, so that in every neighboring time step, we can only move any facility at a distance at most b. As an extension, we can also generalize this definition to the outlier version, also known as the robust version, where at every time step we are also given an lower bound LT, so that we are allowed to exclude some of the clients and serve only a number of LT clients. And our objective will be taking the maximum over these served clients, regardless of other clients as outliers. And in fact, the first one we want to present is a negative result for t larger than 2. We have the following theorem. There is no polynomial time algorithm for solving dynamic k-Supplier with any approximation ratio, even if this approximation ratio is not a constant, unless p is equal to np. The proof is actually pretty simple by a reduction from perfect 3D matching, which is known to be np-complete. So suppose we can solve the dynamic k-Supplier for t at least 3, and we are given an instance of perfect 3D matching over A times B times C, and E is the set of triplets. We will build an instance of dynamic k-Supplier from this instance of perfect 3D matching and show how we can use the approximation algorithm for dynamic k-Supplier to solve the perfect 3D matching problem. We build a tripartite graph whose banks are x, y, and z, which are initially empty. And for every triplet in E, for example, A, B, and C, we add 3 new vertices, A sub E, B sub E, C sub E, to the 3 banks of G. And we connect A sub E, B sub E, and B sub E, C sub E with edges of length alpha, where alpha is the approximation ratio of our algorithm for dynamic k-Supplier. And after finishing adding all the triplets for every single element in A, B, or C, we form a clique using vertices previously added to the graph that are corresponding to the element, where A, B, and C all have 2 elements, and there are 3 triplets in the candidate set: A, B, C, A, B, C prime, A prime, B prime, and C. And this tripartite graph will be the result of the reduction. Obviously, there is a perfect 3D matching of size 2, A, B, C prime, and A prime, B prime, C, which are in blue in this graph. And now to further build a dynamic k-Supplier instance, we need to treat the 3 banks in the tripartite graph as if they are in 3 different time steps. For example, at t equals 1, only the vertices in X can be clients or facility locations. So the total number of time steps is 3, and we define the movement upper bound to be alpha. So now if there is a perfect 3D matching, then this perfect 3D matching will actually correspond to a solution to the dynamic k-Supplier problem, where if at every time step we take all the points at that bank to be clients, and any facility can appear at any location as well. So in this case, because there exists a perfect 3D matching, for every vertex in the graph, exactly 1 vertex in the clique will be selected as a facility location. So the distance from this vertex to this selected location will be 1. And the objective for this dynamic k-Supplier will be 1. And if there is not a perfect 3D matching, for every possible combination of n triplets, there will be at least 1 clique so that none of the vertices in the clique is chosen as a facility location, because the n triplets chosen did not cover them. And in this case, every vertex in this clique will be at distance at least 2 alpha plus 1 from the nearest location in its time step. Therefore, the difference between having a perfect 3D matching and not having a perfect 3D matching is larger than alpha. So if our approximation algorithm has an approximation ratio of alpha, it must be able to distinguish between the 2 cases, which means we can use our algorithm to solve this instance of 3D matching. Hence, P is equal to NP. Next, after showing the negative result, we consider dynamic k-Supplier with the presence of outliers. We also designed an algorithm for dynamic k-Supplier with t equals to 2 and no outliers. And it's pretty straightforward, so I will not include it here. So again, in dynamic k-Supplier with outliers, assume the optimal solution is already known exactly to us because there are only a polynomial number of possible solutions, and we can afford to guess. So let's first recall the definition of dynamic k-Supplier in this case. We have 2 client sets, C1 and C2, 2 facility location sets, F1 and F2, 2 lower bounds of clients covered, L1 and L2, and we need to select 2 multisets of facility locations, A1 and A2. The objective is the maximum distance from any served client to its closest facility over all time steps and over all served clients, as long as we can serve L1 clients for the first time step and L2 clients for the second time step. Because every facility is only allowed to move a distance at most b, we can restrict our attention on the edges between F1 and F2, which have size at most b. And the optimal solution will be something like a matching of size k on this set. But since we allow the use of multisets, there might be some vertex matched multiple times in the solution. For now, let's just assume that no client will be served multiple times by any facilities at the same time. What I mean is, for any facility location, if you count the number of clients it can serve within some distance, like R star, there will be no overlap between any pair of different facilities. And if this is the case, we exactly have an instance of so-called two anti-budgeted minimum matching. And I'll give the definition here. Given a bipartite graph, every vertex, either on left or right, is associated with the budget value, and every edge between the two sides is also assigned a weight. And for the two given antibudgets L1 and L2, we aim to find a matching of minimum weight so that the total cost of vertices it matched is at least L1 on the left side, and the total cost of its ends on the right side is at least L2. And there is actually a bi-criteria algorithm for solving this problem, meaning that we might violate the two antibodies by a small fraction and get a constant approximation, but we still have some problems to solve. The first one is the involvement of multiset, and we can solve it by using the same technique we used in the previous section. And the second one is how to avoid counting the same client multiple times. Well, first of all, if you split a facility location into multiple copies, you do not want to assign the same number of clients it can cover onto all these copies, and you only want one of its values to be positive. And the same goes for different facility locations. And here we use a greedy algorithm for pre-assigning the clients to one of its nearby facilities. And since every client can be assigned only once, it will be counted at most once as well. And after making copies of these facility locations and assigning clients to them, we actually use a new LP on the set of new vertices. And this time we designed the LP to directly solve the previously mentioned two anti-budgeted minimum matching. And we can also provide a bi-criteria 3 approximation algorithm for dynamic k-Supplier with outliers. This problem is in spirit very similar to the multi-budgeted optimization problems discussed before, but there are a lot of subtle technical details we need to deal with once we added all the combinatorial constraints of clustering, which was not present in the original problems. And that wraps up the second part of this monologue. Thank you for watching, and I'm looking forward to your questions and discussions in the online session.